Hello, hello everyone. Welcome back to this soil hydraulics chapter. We have left at this point. We were discussing boundary conditions for flow net. Okay, I'll just read it out once again. The upstream and downstream surfaces of permeable layer are equipotential lines. Permeable layers are equipotential lines. The flow lines intersect with these equipotential lines orthogonally. That is known. Now, the boundaries of impervious layers is a flow line. Permeable layers are equipotential lines. Impervious layer surfaces are flow lines. So also the surface of impervious sheet pile or dam section, if there is an impervious section, then it is a flow line. Equipotential lines intersect these flow lines orthogonally. Okay, these are the things. How to apply these while drawing flow net, we'll see in detail. Okay, these are the guidelines for drawing flow nets. We'll quickly go through these points and then straight away apply them in drawing the flow net. It is easy. Draw to a convenient scale the cross section of the structure, water elevation and soil deposits, right? So here you should make a very clear picture that it is a graphical method. You have to draw the things to the scale, not that you sketch, right? So you have to use some scale and then draw everything to scale. So this is a graphical method, it is not analytical method. So that is very clear. You have to take some scale, space scale, that 1 centimeter equal to 10 meters, 1 centimeter equal to 5 meters, like that. Whatever convenient scale is there, that has to be chosen, and you have to draw the cross section or whatever section. If it is a earthen dam, you have to draw that dam, right, to some scale. Or if you have retained water because of the sheet pile, like that, if there is a water standing on the other side and there is water standing on the downstream side also, so this way you have to draw the sections to some scale. Means what is the height? Suppose if it is 10 meters, so you have to choose some scale. Suppose it is 1 meter, so you have to choose some scale. Like here in earthen dam, here there is a water level. Okay, now what is the height of the dam? What is the width at the top? What is the width at the bottom? If there is a filter which is provided at the downstream end, what is the length of that? What is the slope over here? What is the slope there? So all these things have to be taken into consideration and draw this picture, draw this to scale, right, to a convenient scale in your drawing sheet. That is what is the first point is. Okay, establish boundary conditions, that is identify impermeable and permeable boundaries, because you know that impermeable boundary represents flow line and permeable boundary represents equipotential lines. The soil and impermeable boundary interfaces are flow lines. Impermeable boundaries are flow lines. The soil and permeable boundaries interfaces are equipotential lines. So here in this case, if you look at this is a soil deposit. Of course it is a permeable one we are considering. So surface of soil, that is this particular inclined line, will be indicating equipotential line. Now suppose this is constructed on a permeable layer, permeable deposit, and after some distance there is a impermeable layer. This is impermeable layer and this is permeable layer, right? Now what happens is this surface of impermeable layer, this surface becomes flow line. This becomes a flow line, right? So like that you have to analyze. These two are important points, permeable layer and impermeable layer, which one is there. They will be giving you correspondingly equipotential lines and then flow lines. Draw one or two flow lines and equipotential lines near the boundaries. This is a sketching, it's a trial that you have to make, right? Sketch intermediate flow lines and equipotential lines by smooth curves adhering to a right angle intersection such that area between a pair of flow lines and a pair of equipotential lines is a curvilinear square. We have discussed this. Suppose if you got two flow lines and you should have equipotential lines intersecting perpendicular to the flow lines, and then one more, when you draw it, you make a trial and error and make sure that this is a curvilinear square, means you should be able to fit in a circle which will be touching all the four sides. That is what this particular point means. Now where the flow direction is straight line, if there is a space like that, here you have below the earthen dam almost horizontal flow is there, so straight line it is. A flow line is a straight line. Now where flow direction is straight line, flow lines are equal distance apart and parallel. Okay, try to avoid making sharp transition between straight and curved section of flow and equipotential lines. Transition must be gradual and smooth. What it means is, for example, this sheet pile case, if I take, and then if the flow comes here, enters, and then it has to go and then join there. So you cannot make the flow line like that, straight down, a sharp turn, and then again a sharp turn like that. So water will not be able to take a turn like that. So this has to be a smooth transition. That is what the point says, right? Successive trials will result in a reasonably consistent flow net. In most cases, 3 to 8 flow lines are usually sufficient. The number of equipotential lines will automatically be fixed by geometry and grid layout. Okay, so these are the points which are to be remembered while drawing flow net. Okay, we'll go to the next slide. Okay, here the same boundary conditions are written here. Now what is to be done here is, what is asked is, there is a weir which is resting on pervious strata. There is a pervious strata wherein the flow is occurring, and there is an impervious strata. So this is impervious. You can see that there is a strata impervious. So this is the surface of impervious, and this is a ground surface. Of course this layer is pervious, right? And this is a concrete structure. Now if you want to see it in third dimension, so it will be looking like that. Fine. So this is a surface like that, surface like that, having vertical edge over here, vertical edge, vertical edge, vertical edge. Okay, so this is how the concrete structure is, right? We have a section of that, and there is a upstream water surface on this side. This is called upstream because the flow is occurring from left to right. The flow is occurring this way. So we have made an arrangement where water has to stand behind the structure. So there is some head with which it is standing, and here on downstream side I haven't shown any water standing, so it just comes and then flows off, maybe, right? Sometimes they may give you a standing water at slightly lower level, so that that difference in head will be pushing the water through the pervious layer. Now what you should observe here is, that's an important point that I would like to mention, because I haven't done step-by-step animation. You have to understand it, that's all, right? Okay, here upstream, downstream. If you look at the points there, boundary conditions, upstream and downstream surfaces are permeable layer. Okay, where the surfaces are here? This is a permeable layer. So the top surface over here is a permeable layer. Of a permeable layer is a equipotential line. So this line represents even on this downstream side, this surface also represents equipotential line, right? So, and whatever line that I am trying to draw this way perpendicular to that, so this line will be obviously flow line, because you know that equipotential lines and then flow lines intersect. So when it starts off, you have to take care that this is 90 degrees. So as much as possible you make it as 90 degrees, and then here below the weir there is a space where the flow is occurring almost horizontally. So almost equally spaced flow channels are there, or flow lines are there. So whatever black lines you are seeing, they are flow lines. Approximately you can insert, as told, 3 to 8 flow lines are sufficient. So you can devise, right? So equipotential lines, once they are fixed, you can start off to draw number of flow lines as per the convenience. Okay, and then next important point to be remembered here is the boundaries of impervious layer is a flow line. So this is an important part. So concrete structure, weir is there, the bottom of the weir is a flow line. So that's an important point that guides you for drawing. Look at this surface, and up there. So this is the surface along which the flow is occurring. The flow is occurring in this direction. So this indicates a flow line. Also, here there is an impervious layer, the surface of which is a flow line. The surface of this impervious. So this is also a flow line which is moving that way. And in between these two, I have black lines which are indicating some more flow lines. So this we have to make by trial and error. So I have inserted between the top flow line, bottom flow line, I have inserted 1, 2, 3, 4 flow lines, right? So, and then by sketching, you have to make and come and touch the equipotential lines perpendicular. So it is a graphical method wherein you have to draw the sketch, erase it, draw it, erase it, like that. It's a trial and error method. So method itself is known as trial and error method or graphical method. And then look here, we have first equipotential line, flow line, intermediate flow lines. Now you insert these red equipotential lines such that this is an approximate square, this is an approximate square, this is an approximate square in the sense I should be able to insert a circle which will be touching the all the boundaries, right? At extreme cases you will not be able to do it, but when you come to the next equipotential line, it should be such that you will be able to draw the square like that, circle like that, touching all the 4 sides. So that way you have to insert these equipotential lines. So that is an art. So it comes by trial and error. So you have to insert all these equipotential lines such that continuously they intersect the flow lines perpendicular. Moreover, they are squarish. These flow elements are squarish. So that's how one has to complete all the equipotential lines intersecting the flow lines, and then this whole set of curves is known as flow net, right? Okay, this is a case where weir is there on a permeable layer sitting on impervious strata. We'll see one more. Okay, here there is a sheet pile. you can just see here what is meant by sheet pile in third dimension. If you want to see, so there is a sheet like structure which is driven into the ground, right? So water is standing at this level, the bottom is being seen there, right? So this is the water surface. On the upstream side there is a water surface there, okay, and there is a pervious strata. You can just see here all this is a pervious strata sitting on impervious layer. So by these points what we can do is, it's a permeable layer, so I have an equipotential line at this, Next important thing is the surface of impervious layers are flow lines. So I have first flow line which is touching this and then going like that. It should be touching. It comes down there, it goes, takes a sharp turn, and then it goes up. This is a flow line. Again, surface of impervious, this is impervious layer. The surface of that is also a flow line. So this is the line along which the flow can occur. So you got one flow line which is touching the sheet pile which is driven, sheet like structure which is driven into the ground. On one side you got standing water, on the other side you got standing water with a lesser head, right? This sheet surface which is impervious is a flow line. The top surface of impervious strata is also flow line. Now in this case, in between I have to insert some more flow lines, and I have inserted three flow lines I have inserted, and then I have to gradually sketch backwards and then go and touch this equipotential line in such a manner that it is 90 degrees over there. Again, there is a second flow line I have to sketch and then join this so that this is 90 degrees. Again, here also you take it and then join so that this becomes 90 degrees. Similarly, on the downstream side also you can extend the lines and then join the equipotential line perpendicularly. After this, again you have to draw equipotential lines. What is the idea? The elements that you create are circular squares, so that way, and then moreover the flow lines, equipotential lines will be perpendicular to the flow lines. At that point you have to keep it in mind and then go on drawing these red lines. So they will be indicating equipotential lines. Care has to be taken, erase and redraw such that the elements that you create are squarish in nature. So that becomes Flownet. Now what is the counting that you have to do is, we want ultimately NF, which is number of flow channels, not number of flow lines, keep it in mind, number of flow channels and number of drops in the Flownet. We'll count in this case, right? So here in this Flownet, if you go on the downstream side, from this equipotential lines to this equipotential line there is one drop. From this to this equipotential line there is one more drop. There is one more equipotential. There is one more equipotential. Like that, you got drop number 1, drop number 2, drop number 3, drop number 4, 5, 6, 7, 8 when it reaches. So number of drops that I have in this Flownet are 8. So number of drops in this case are 8. Okay, we shall count the number of flow channels. It is easy. We need not look at number of flow lines. The space between the flow lines is known as flow channel. So here at the bottommost there is one flow channel, 1. Here there is 2, that is the one. There is 3, that is the one, and there is 4. So you got 1, 2, 3, 4. So number of flow channels that we have in this case are 4. So in the problems, if they give you number of flow lines, you have to subtract one, because you can just see here, there is number 1 flow line, number 2 flow line, number 3 flow line, number 4, number 5. So 5 flow lines make 4 flow channels. Similarly, equipotential lines, the top one, 2, the 3, 4, 5, 6, 7, 8, 9. 9 equipotential lines make 8 number of drops. So this one has to be very careful. So like this information has to be got from Flownet. Okay. Okay, there is one more case wherein there is a weir with a cutoff on the upstream side. With the same idea, you can try to draw the flownet on your own. You try to sketch off and then see. The black lines indicates flow line. The red lines, of course, this is also a red line because it is an equipotential line. Even this is an equipotential line, right? So black lines, even this line, because it is an impervious layer at the bottom, and only pervious layer is this, right? So here we have all these black lines which is touching the surface of concrete, and then sheet pile is a flow line, next flow line, next flow line, next flow line, right? You can just see how the idea of flow line will be. It is not exactly taking the shape of the structure. Slightly it goes and then it touches, it should touch rather here at 90 degrees. That care has to be taken. This is not proper here, right? So this is fine here. It is 90 degrees almost. Even here when it joins, it should have been like that, so that this is 90 degrees. Okay, anyway, that gives you an idea of how to draw the flownet. There is one more with a downstream weir with a downstream vertical pile. Now how to draw. So here there is a mistake, but anyway, you have understood. Here it is good, like it enters almost at 90 degrees there, 90 degrees there, and in between you will be having 3 to 4, 3 to 8 actually, but 3 to 4 is sufficient for our cases. Okay. Okay, we'll discuss about exit gradient. Of course, maximum exit gradient. What is it, and then what is the use of it, etc. This discussion is obviously relevant for or relevant with flownets. You have already flownet drawn here. I'll explain you the conditions. Here there is an impervious rocky layer. This is the top surface of impervious layer, and then here you got pervious layer wherein flownet is drawn. We'll show that soil pervious layer, and then there is sheet pile which is driven into the ground. It is sheet like structure which will be driven into the ground so that it can store water on one side. There may be water standing on the other side, or there may not be water standing, but invariably there will be a water standing on at least one side, so that the structure itself is for the purpose of retaining the water on one side. Now in such condition, what happens is the water gets penetrated into this, infiltrates, and then it tries to come up like that. So that is what we have studied, and then we can draw a flownet like that. This sheet pile, actually when we draw the section, we just show it as one thin line, double line like that. So one should understand that it is having a dimension like that. Okay, now here I'll remove all these things so that clearly you can see. I have taken just like that. arbitrarily 12 meters over here, 1 meter standing water. And then this is impervious sheet pile. Obviously all along this periphery there will be a flow line. This is impervious surface. All along this there will be a flow line. In between I have instructed 1, 2, 3, 4 flow lines. And this is a permeable layer. So surface of permeable layer is an equipotential line. So whatever 4 flow lines I have made, I will just gradually take them up and then make sure that when they join at 90 degrees there, right? So somewhere it has not been done, but you have to take care that you have to join it at 90 degrees as much as possible. So the curvature has to be smooth enough. Then after drawing all the flow lines, we have to insert equipotential lines, right? This is an equipotential line, this is an equipotential line. So parallel to that, slightly adhering to the condition that equipotential line intersects the flow line at 90 degrees. Wherever there is an intersection, you have to see that it is 90-degree intersection. With that condition, you have to insert number of equipotential lines. So I have completed that. Now here you can just see how many drops are there. There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 drops are there. So I have taken 10 drops. Now how much is the head that has fallen? It has fallen from 12 meters to 1.5 meters. So the head difference, 12 minus 1.5, which is 10.5 meters, is dropped in 10 steps. So each drop, which is equal, is of the order of 1.05 meters. Irrespective of the distance traveled, look at that, though the distance is less somewhere, but there it is large, but the drop from one intersection to the other intersections are from one equipotential line to the other equipotential line. The drop is to the tune of 1.05 meter. Now the idea is exit gradient, hydraulic gradient. By definition we know that it is H by L, represented by the letter I. So I, which is head lost in a length L, L is the length of the soil in which that head is lost. Now here we have seen that 1.05 meters is the head lost. Even here, anywhere if you take from this point to this point, when the water travels along the flow line, it loses a head of 1.05 meters. But the length for which it has gone is more. Now if you calculate hydraulic gradient for this, what happens is that 1.05 will be in the numerator, denominator will be having this length. Now if you take over here, the length is less, so numerator becomes 1.05 fixed, 1.0, because drop is 1.05 from this equipotential line to this equipotential line. The drop is 1.05. Now you have to search for a point or a location where the distance traveled or distance between the equipotential lines is least. Obviously it is nearest to the sheet pile wall over here at the region A. Right here by scale, you know that the section has to be drawn to some spatial scale, and then by scale, let us say this distance is of the order of 4 meters at A, that is at this particular flow element. Exit gradient I with a suffix E, exit gradient at point A is equal to, this is drop, right? How this drop is 10.5 was the original head difference. From that 9 drops already gone, the leftover head will be 1.05 and in a length of 4 meters. So 1.05 divided by 4, that gives you exit gradient at A, or is 0.2625 exit, because after this it is coming out. That's why it is exit gradient or hydraulic gradient with which the water comes out from the soil surface on the downstream side. So that is 0.2625. Now if you take next uh, flow element or flow region over here what happens is the distance will be more. The numerator will be 1.05, but this distance will be slightly more, maybe 4.5 meters. Here maybe it is 5.5 meters. Here maybe it is 8 meters. Depends, right? So your numerator value goes on increasing as you go away, or the distance traveled by the path of flow line will be more and more. Because of that, more the length in the denominator will be having lesser the hydraulic gradient. So if you want to search for maximum exit gradient, you should be nearest to the nearest to this sheet pile wall or any structure, right, on the downstream side, nearest to that surface, nearest to that impervious surface, we should search for. If you go farther away, then you'll be having lesser exit gradient. That is it. Okay. Now here the same thing is there, maximum exit gradient, sheet pile walls. Here there is you can just see how to calculate. There is a thumb rule. Maximum exit gradient for sheet pile walls can be computed alternatively as explained below. A theoretical solution for determination of maximum exit gradient for a single row of sheet pile structure is available and is of the form 1 by pi h1 minus h2 divided by LD. LD becomes length of depth of penetration. This, how much is that sheet pile which has entered into pervious uh, pervious strata, that is LD, depth of penetration, that has to come in the denominator. This gives you an empirical value of exit gradient, I exit. Of course you have to have a single sheet pile. You cannot have number of sheet piles driven parallel to one another, then the case will be different, because this particular expression is for single line of sheet piles. Okay, with this we'll stop. Thank you.